Um, Welcome to CS205 to our prospective students. This class is about parallel programming. We've been talking about GPUs. Today is basically our wrap-up lecture on GPUs. We're going to talk about a couple of techniques to make them faster. It's also a review for questions that people have had. Yeah. All right, so homework 3, due November 18th. Several people have already committed their answers. That's cool. We sent out peer reviews for homework 2. This makes the TFs ask for this. It makes it much easier to grade. So please do a quick review. It doesn't have to be very in-depth, but please do that soon. The sooner we do that, the sooner we'll be able to grade homework 2. We won't do a peer review for homework 3 just because it'll be too close to the end of the semester. Final projects. You should have already met with your TF or scheduled a meeting for the near future. Plan to check in at least once by week, by email or in person. That's at the discretion of your TF, what they want you to do. And each milestone after the first meeting should include some code, some results, something basic, showing that you're able to, process the data, get it into some form, showing progress towards the final project, okay? So, but include code as part of that. TFs know this, and they'll ask for it. I encourage you just to work on GitHub and groups there. It's probably the easiest way. If you don't want to do it in public, then you can figure something else out, but that's really far easier and then easier for the TFs as well. And then you can also use the GitHub pages for setting up your final project website and stuff like that. All right. So today we'll just do the OpenCL review and GPU wrap-up. After this, it'll be just more random topics about various parallel techniques. So atomics, there was a question. When and how to use them? When are they useful? What are they good for? How do you apply them? So we'll go through an example using corner detection. So a pretty common image processing technique. So we have some image. And often, if you're doing any sort of multi-image processing, in particular if you're trying to do some sort of camera tracking in the scene or extracting geometry, you'll go and you'll take the image, and the first thing you'll do is corner detection or some sort of feature point detection. And you'll find a bunch of points in the image. You'll extract some sort of descriptor from those points, and then you'll have another image later on or from a different time, from a different viewpoint that you'll want to match. And so the first step is just find distinguishing points within the image. So we can load this image down to the GPU pretty effectively and then do this processing in parallel across all the pixels. But then we need to get the corners back, or we need some way to store them. And we don't want to store them in the image itself. We don't want to read back the entire image. We want to reduce it down to just the information we care about. So just the list of corners or some small list of corners based on which ones are more interesting or have greater intensity variation or something like that. So we want to condense down the data for transfer or later computation. So what we'd like to do is have this corner location array on the GPU. And we'd like to take each corner we've detected and copy it into that array. All right, so this one, at this location, we go with the first spot maybe, and then this one over here, we go with the next spot, and then all the other ones into this much smaller data structure than the image itself. But, so how would we do this? Well, we have to allocate a buffer to store these, to return the locations or store them on the GPU. And we have some limits, right? We can't do more than however much we allocate, right? We're on GPUs, so we allocate, the CPU handles the memory management and says, okay, detect up to 1,000 corners, allocate some space for that. And we're also in this multi-threaded domain where we have thousands of threads or a thread per pixel operating, and they have to cooperate to fill that buffer, right? And they're running at all different times, so we don't have any sort of synchronization between those threads. So some threads might, if they're operating within a window, some work groups or thread blocks or individual threads even, depending on how we implement it, might detect more than one corner or no corners. And so we don't know where each thread can write its output, right? We don't want this buffer to be as large as the number of threads we have, which would be one solution. Have each thread only able to detect one corner, and then it has a fixed location to write in. But because that would be probably the size of our image, right? We are in the domain where we have a thread per pixel, roughly. All right. So our data is gonna, something's gonna happen like this. We're gonna have, let me go back to the image. we're going to have some block of threads running in one location of the image, and it's going to detect some, and it's going to produce a list internally to its own memory within its registers or local memory or something. And then it needs to store those back to the global structure, right? So for example, thread 1 says, I have a corner. Thread 2 says, I have a corner, it's at this location. And thread 3 has some other corner. The way we're going to solve this is we're going to have a global count. It's going to be stored in global memory. We're going to access it with atomics to make sure that we cooperate, right? There's no way that these can know where to write their data. What we'd like is, okay, some thread comes in and says, okay, how many corners have been found so far? And says, oh, 0. That means I will store at entry 0, my corner, and I'll increment the number of found corners, right? And so when another thread comes in and says, okay, I found a corner, where do I store it? It says, oh, well, there have been 1 found, so store it there. Increment the counter, and then the next thread goes on, stores there, increments, all the way until it's full, or until however many we've done, right? We can't do this without some sort of synchronization or atomic access to the num found variable, right? If we don't have some sort of synchronous access, what will happen? What will happen if that's just a global variable that we store and a bunch of threads come in? What's going to happen? Right, it's going to get overwritten. One of them's going to, some thread's going to say how many have been found? 2. Some other thread's going to come in at the same time and say how many have been found? 2. They'll go in and they'll write their data to location 2. They'll both increment it, and it'll think now there are 3. And quite possibly, we've experimented before with just sort of lazy locking or lack of locking, where we write a value speculatively and it might get overwritten, but we're not too worried because it's always just like one integer. But corners have more information, right? We're probably going to write its location, its color. There could be a lot of data written here, and if we do that speculatively, some part might write, and then another thread comes in and overwrites the whole thing, and then the next thread writes its last half of information, right? So we don't even get valid data, right? We use that technique actually in the in the maze solution, right? Where we didn't have to worry about that, where it's just single integers being written, and if they overwrite, we're always going to have a valid value. You don't write half a word. But in this case, it could be quite bad. All right. So the atomics will allow the threads to keep from overwriting each other's work. We'll always do an atomic update to the number found. We'll always get a unique location from that, and we'll also be able to check that we don't overwrite the maximum. Now, the code's not really very difficult. It's pretty simple. I mean, the idea is a little more complicated, but what we actually do is not. So, did I mark up this code? No. So, I called this sum. It shouldn't be called sum. Okay, so we have an image. We have some buffer to store the corners. That's the output buffer. We have a global integer, which we've allocated on the host. So it's a location in memory. We have a pointer to it. It's the number found. And we have some maximum, which is the size of our output buffer. We can't find more corners than that without overriding the memory. So we do our code to locate the corners in the image using whatever technique. And then, just in pseudocode, every corner that we find, we do this. Atomically increment number found. Right, this is a memory location because it's a pointer up there. So here it's a memory location. It goes and fetches the value, increments it, and returns the old value. So this starts out at 0. The first thread that calls atomic min will get a 0 back and store a 1. And that will happen atomically. That means that no other thread can get in there. The first thread goes in and says the value is 0, increments it to 1. No thread can come in there and get a 0. If the next thread that gets access to that memory will read 1 and set it to 2. So we increment that. And then we can also just check, okay, where was I supposed to store it? Only if I have space, then do so. And I might have how many corners did I actually detect, some other global variable here that I would use atomic increment to, oh no, I already have that. At the end, I can check, I can read back the number found to see how far did I override. How many corners do I actually have to read? It was you that asked how to use atomics, right? Does this explain? This is one of the basic cases. There are other ones, where you've got multiple threads writing back to data. I didn't talk about it here, but often what you'll want to do is, do all the work, or if there's some sort of reduction that's involved in these atomics, do a reduction or some sort of condensing of the work in the work group, where you do have some sort of synchronization. You have local memory. You can use atomics on local memory, but you keep all of the communication local first to condense down your answer, and then use atomics to global memory. Because just like local memory is much faster than global memory, and communication between threads within a work group is much faster than, well, you don't have any other communication, but it's fast. You can reduce the amount of communication necessary to global memory. You reduce basically the number of atomic calls. Because global memory is slow, understandably, atomic calls on global memory is even slower. I'll post there's an article on, this sort of work group reduction that you do. Yes?
So 2 questions.
Yes.
One is, so this IDX thing works because atomic increment returns like the value that before you increment.
In this case, yeah. Almost all of them return what used to be there.
Right. Okay.
Yes.
And question on what you just said. So if you did that reduction, you'd want to like count all the corners you can find within a work group.
Yep.
And then sum that up, and then increment by that. So you're only doing global memory once per work group, right?
Right. So, for example, what you might do, actually, I think maybe I've used atomic increment wrong here. Someone can check the docs, but you might have to give a number. Or there's some other one where you can increment it by a certain amount. So in that case, what you would do in your work group is say, how many corners do we have? 20. You would increment it by 20 in one global call, right? You'd get the index of the start of where you should write those, and then you basically say, okay, well now I know I can start here, I have 20 space that I've allocated basically. And then you distribute those out to your threads who then can write independently, right?
But so when you're tallying up within the work group,
Yep.
do you have to worry about locking local memory, or is that automatic?
So do you have to worry about locking local memory when you're tallying within the work group? Yes. We don't have locks in GPU land, but we have atomics. We also have knowledge about so we can still use atomics. You can use atomics on local memory. They'll be faster than using atomics on global memory because local memory is close. You would probably use some of the same techniques as the parallel reduction in homework, in problem 3, where you don't use locking. You just use the fact that you know things about your indices in your local group, and you can make sure that you're using a piece of memory that no other thread in your work group is. So locking or atomics or just smart, basically thread location math. So you could do that more efficiently, and then just make one big call to, one atomic call per work group to global memory. Other questions about atomics?
Both reading and writing.
Reading and writing are both slow when going to global memory. Atomics are going to be even slower. I'm not sure what the sort of back and forth is with atomics, but it's not going to be faster than just a normal write.
What are operations?
Max, min, XOR, exchange. There's about 8 or so. You just search for the OpenCL. OpenCL has atomics. CUDA has different atomics. The overlap is about 100%. But a bunch of basic algorithms that are basic, very simple things that you could do. Atomic XOR, maybe. That doesn't make sense. What's that? Is there a way to stitch them? Oh, to do multiple atomics? No, not really. You could implement, well, you can't even do that. Could you implement a busy loop? You could implement a busy wait, yeah? Oh, okay, he'll talk about it on Monday. He's going to lecture on Monday. Give me a break. You could, there are ways you can probably implement some things, but you have to remember also that we don't have locks partly because we have threads all over the place, and they're scheduled independently. So if it's quite possible to get in a very bad deadlock situation where one thread grabs the lock and then for some reason stalls, and then all the rest just can't do anything. And it's unclear to me whether in a GPU situation you could have a thread that just stalls it forever, right? If the other one's for some reason, I don't think so. But it's not something that's done. It's not gonna be efficient on GPUs, so it's not gonna be the right approach usually. Okay. Other questions on atomics?
It's not about atomics, but just a question about when you specify the type of the inputs, the global.
Yep.
Do you get performance improvement by specifying like read-only or write-only?
You have potential performance improvements. You also have some, the question is, does it help to say read-only, write-only, read-write? I don't think, is write-only an option? Maybe. Does that improve performance? You potentially improve performance. It depends on the back end and what hardware it's running on, whether it allocates memory in a different way. It gives you possibly some error checking as well, where you try to write to something that's read-only. But it's really vendor dependent, both hardware and OpenCL, whoever implemented it. So it's not a guaranteed thing. It is informative to whoever's using the code later that this data is, I'm only gonna look at this data, and if I modify it, then bad things could happen. Yep. Anything else for this? Okay. There are questions, and several people asked, okay, we've done a lot with kernels, let's talk about the Python upper level, PyOpenCL. So basically the Py part of PyOpenCL. This is the standard sort of structure that I'll just walk through quickly with a very simple example of the Python program above the kernels. Right? You find the platforms and devices. Usually there's only one platform depending on what you have installed, but usually only one. Some number of devices. My laptop has 3, other people have, it depends on what GPU cards you have, what sort of built-in GPU programming there is, or whether or not it'll adjust the processor, or it will attach to the processor. You create a context on one of those devices, or possibly you can create multiple contexts if you want to process on multiple devices at the same time. Get some queues so you can talk to them, allocate memory, transfer the data down, and then just process, and then possibly read back using the queues. So the platform's devices in context, you get your PyOpenCL, you get your platforms, and then you say, okay, I'm gonna get the devices from a particular platform. Usually you'll just do this, platforms of 0. There'll be one platform. This will return a list, but you'll just have one element. Find all the devices, and then you may have to do, depending on which device you want to use, you may have to actually put a value in here. Some people have been getting crashes when they use on the Mac, if they use the HD graphics installed and not the NVIDIA. And so a lot of people have been having to do this for the homework. All right, so this is basically use the second device that I found on whatever platform.
So you could actually put multiple devices into that context and then you run on them at the same time.
Could you put multiple devices into the same context? You could not put multiple devices into the same context, but you could create a second context where I could have, context 1 equals for device 1, context 2 for device 2. And that would allow me to do some overlap computation on multiple devices. If I had, for example, 4 GPUs, I might open 4 contexts to talk to each one independently and have work going on each of them. This is something that OpenCL actually is sort of trying to push is you might have one just on your CPU as well, right? You might, for the whatever idle processing power you have on your CPU, you'd open a context to do some work there as well. And that's gonna get into load balancing and choosing what the CPU should do versus the GPUs. So it could get quite complicated, but it's possible. So is it up to you to manage the work? Yes, at that point, your Python program is your scheduler. And for almost all GPU programming, it's scheduled above. Not entirely in some of the new PyOpenCL 2.0. I didn't talk about it in this class, but you can actually, you have a Python program or some upper level program that launches programs on the GPU and it starts processing. In the old days, it would process and then you would read back some result or launch another kernel. Now, actually, kernels can launch kernels. So you can, Well, there's a good case for this, so it's a little strange, but basically the kernel can run and then say, oh, you know what, there's some more processing to do. And the classic example is actually something like corner detection, right? Where I might find a corner, right? And I want to say, okay, is this corner interesting? I may want to do some computation around that corner to get a descriptor. And that stuff is perfect for the GPU to run. It used to be that I would do basically what we showed, detect corners, store them in a list, then on that list, launch a thread per element to go back to the image. Basically one less round trip. So now it would say, oh, I found a corner, launch a kernel, or I found 3 corners, launch 3 kernels to compute around this corner the information and then store the descriptor back to this table. So this came out with CUDA a year or 2 ago. OpenCL 2.0 has it. It's nice in a lot of cases. So it's minimized the communication. We'll talk again about, we talked a little bit ago about communication to the GPU is often really slow across this PCIe bus. This allows you to avoid that even more.
So on the homework that you made a context with multiple devices.
So if you pass in multiple devices here, and often you'll just pass in that list, and you have to pass a list, which is why I've selected one out and then put it back in a list. It'll just choose one. Often the GPU or the most performant, whatever it thinks is the most performant. But the problem is then sometimes it'll select one where the support is poor, and that's what's been happening with some people with the homework, where it says, okay, well, I'll use the HD graphics, and then it explodes, so you have to switch it to either CPU or another GPU. All right. So after you have the context, then you set up a queue. You can set some properties. I just broke it up this way to make it readable. We've been using the profiling enable, which has some overhead costs, but allows you then to figure out when your kernels ran and how long they took. You set up a queue, which is just where you're going to launch, you're going to communicate things to the GPU, basically. I'll ask it to allocate data, I'll copy data down or read data back, I'll launch kernels. There are some synchronization methods. You can put barriers in and use events to wait, which I'll show in a little bit. But this is basically your pipeline to the GPU or whatever you're programming to. And then you allocate buffers for whatever problem you need, or whatever problem you're trying to solve. So you'll start usually, I've got some host data from reading an image, or I'll create random data or reading whatever. And then sort of the simplest form is, I need a buffer that corresponds to whatever data I have on the CPU. So you just use this host buff, the context, whatever flags. Flags will be some combination of these. Read, write, read only, all of these make a lot of sense. Copy host pointer. The other ones, it gets more and more esoteric. And you get into things like, okay, we want pinned memory that the GPU device knows exactly where it is so that the GPU can launch copies to host memory without me having to tell it where to write. We're not going to talk about that. If you start doing a bunch of GPU programming, it's worth understanding how mapping works and things, and the more strange flags you can put in here. Yes? Our buffer's always one-dimensional. Yes, they're always a block of memory of some size. It's up to you then to interpret it the way we have done with the sort of image offset math. Interpret it in terms of 2 dimensions, 3 dimensions. But it's always just a pointer to memory. It's this location in memory on the GPU or the CPU going for this long. So yes, it's okay. It's always just a block of memory except when it's an image, which we haven't used. It is very efficient if you're going to do image processing. It can be. And this basically goes into the texture, excuse me, goes into the texture memory, which then has special hardware for things like addressing by 2 dimensions, right? So we don't have to do all those computations. And so if you're doing image processing, it's worth understanding how to use the texture memory for things like this. It also has interpolators sometimes where you can ask for a pixel value between 2 other values or in the center of, not centered on a grid. but offset, and it'll interpolate it in some way using the data around it. Right. So in the simplest form, you can just say, okay, I've got this data, and then on the buffer, just say, okay, copy host pointer, and give it the size, and it'll just allocate and copy at the same time. So if you've got one image that you're gonna do a bunch of processing on, you can just do this if you're not gonna change it. Allocates it the correct size and just loads the data down right then. All right, and then to copy to and from, we've seen this with the, to copy the data to. It's the desk source. It's kind of weird, right? This is where you're copying from. It's always to from. So to the GPU, to the host, from the GPU. You can also copy from GPU to a different location in the GPU, which is sometimes useful. And you may even be able to use OpenCL to copy from host to host, but I don't know why you would. But this might be helpful in some of your final projects. I don't think you need it for the homework. All right, and then we launch kernels on the data.
On the last one, would that be across, I guess, row memories, the two different thread groups?
Would that be, so in this last one, is it across the local memory of two thread groups? No. Local memory is only visible while the thread is running. This is two global locations. But it would run entirely on the actually, I don't know if this last one actually works, but I think it does. And I think CUDA just uses CUDA memcopy or something like that. But it's global memory to global memory, and it probably launches a small kernel to do that.
So do we have to worry about row major, column major, or between NumPy and GPU?
Do you have to worry about row and column major? You do have to understand how your data is laid out, yes. I'm not sure if you can copy row major data, if it'll do the right thing. I don't know what it'll do if you hand a NumPy array that's strided, for instance. You've got a slice or something like that. I don't know if it wants contiguous memory for copying. And actually, now I think about it, I don't know if this is even possible, because these both include sizes. I haven't tried that. I just think I know you can do it in CUDA using various techniques, but usually you have to say this is how large it is. But that should be available to the OpenCL, so I think it's okay. All right, so there's a simple example that I'm gonna walk through real quick. I have all the code in here, basically. It's just from the PyOpenCL example. It's just a very simple demo showing these pieces off. It's got the setup, right? Create two arrays, random of a certain size, as floats. This is a nice little shortcut that we didn't use in class because we wanted to be more explicit about which hardware we're using, and we wanted to look at it. You can just call this CL, create some context. It'll give you a context on some device. It'll prompt you which OpenCL, not context, driver. You want to use which hardware, and then we'll run on that one. So it's useful when you're just experimenting and don't want to have to choose a particular driver. And then just sets up a quick queue on that context. Allocates a couple of buffers, copies the data down as part of that step. Yeah. And then we have this kernel we're going to run. Right, we have the PRG is our handle to the kernels. There might be multiple kernels in this source code that's just inline here. And then sum is the function that we actually call when we launch the kernel. And this one just uses a very simple, just add A and B into result. And we call build to turn this into, to hand it off to the OpenCL compiler. We've got three globals, right? Instead of using read-only, they use const in the example, which also works. And then the global float for the output. And then we've got the very simple per pixel or per value statement. So this is going to launch this is basically the thread per output example. We allocate, then it allocates the buffer for output, and then we call that PRG sum. On the queue that we created, one thread per, this is the global size. It's basically just using the shape of the input array. And then this is something else we haven't talked about, but because we wanted to be more explicit in the homework, but you can put a none. You can just say a global size, and let OpenCL choose your local workgroup size according to what the hardware likes. And it tries to optimize in various ways. But you don't have to specify it in some cases. I think you still have to be able to, I don't think you can set for example, a really large array of a prime length, I think will cause this to crash because it can't find a good tiling size. And you do have limits on how large your local size can be. But in general, you can just do this. Let it choose the local workgroup size. And then our 3 arguments, the 2 inputs and the output. And then after it runs, right, allocate an empty array to fetch back the data and enqueue a copy on the same queue. Right, is that enough? That's the Python talk. Using the simple demo program as a skeleton is a good way to start in a lot of cases. Yes?
So A and P shape, that's what specifies number of workers and number of workgroups.
The A and P shape is our global size. So that's the total number of threads that are going to run. And usually what we've done is in that next argument, we said how large of a local workgroup, right? With the requirement that the local workgroup in whatever dimension we just define has to tile the global workgroup, right? And that's why we sometimes have a few extra threads hanging off the end outside the image, but within the global workgroup. In this case, we let OpenCL divide it up into some reasonable size. And it will just do it automatically if it can. If it can, it'll fail. Is there a limit on the number of threads? Yes, it's pretty high. I forget what it is for NVIDIA. There are limits, but it's something like 2 to the 16th in each dimension, up to 3 or higher. It'll let you do a lot of threads. It's take a long time. But, the local group is much more constrained, often less than 1,000, sometimes less than 256, sometimes no more than 512 total in whatever, however you want to split that up in 2 or 3 dimensions. Okay, other questions about the Python skeletons? To launch multiple parallel kernels. 2 ways to do that. One I'm going to talk about. The other one is out-of-order queues, which I'm not going to talk about, which is an OpenCL 2.0 thing, also an NVIDIA thing now, where you can use a queue. Usually in a queue, it's a queue. You launch it, you put in a copy, you put in a kernel, you put in another copy. They all run in order, and the next step doesn't start until the previous one finishes. Out-of-order queues, it's whatever's ready, and you specify which events to wait for. It's a more complicated version of what I'm about to talk to. Well, I'm going to talk about another way to do it using multiple queues. With the out-of-order queues, which require 2.0, you can do something else, and it uses a similar thing, but we don't all have OpenCL 2.0. So last thing I want to talk about is overlapping compute and communication. This is the drawing from last lecture, maybe 2 back. In our standard setup, right, we've got bandwidth, a lot of bandwidth, GPU to its own RAM, very poor bandwidth to the GPU, and then in between to the CPU's RAM. So anything that we do on the PCIe bus, any transfers that we do, take a huge hit, and we want to avoid that. As I said, the default behavior in OpenCL and CUDA is for each transfer to finish before the next whatever is on the queue starts. And so what that looks like when we have this, we're going to set, for processing video, for example, we send down a frame, do some processing, read back some result, send down a frame, do some processing. It looks like this. And those big gaps between the green blocks of compute are wasted. Right? Nothing's going on there. Right? And these are slow. Right? These all run at 16 gigabytes a second. And these, the communication speed, have a 200 or more gigabyte a second processing. So it's quite possible, actually, that if this is a large data set, the width of that red block in terms of time could be larger than this, right? If it's a memory-bound kernel without a lot of compute, then you scale it down by how fast you can go to memory. All right, so it could be that the picture could be just a bunch of really thin green squares filled with empty white space of no compute. But if we look at the dependencies in this processing, right, we can't start that compute until the copy is done. And we can't read back the result until the execution is done. But there's nothing that says we can't start this copy before this other copy, or anything in that chain, right? That next copy doesn't depend on anything before it. So why don't we just do this, right? Start all our copies, start the processing as soon as we can, and then copy back as soon as the result is ready. As soon as this, that second green square finishes, we can copy back the second red square. Yes?
Well, wouldn't your red block get blocked by the blue block being sorted?
Well, the red blocks are blocked by the green blocks, right? This red block can't start till that green block finishes. That green block can't start until that blue block finishes.
Right, but aren't the blue and the red using the same path to transfer data?
Maybe, yes. Communication buses aren't always shared directionally, but it's quite possible that yes, there's going to be contention for reading and writing going against each other. But also, if we use the techniques that we talked about, and if we're doing like video processing and frame matching, then there may not be any readback, or maybe every 20th frame or something like that. We probably want to condense down what we're doing, so the blue blocks are large and the red blocks are very small, or only happen every 20th frame or something like that. But yes, there'll still be contention. How do we do this? Well, we just create multiple queues. We'll set up 3 queues to the same device, same context and same device. We'll have a queue that writes down, a queue that executes something, and a queue that reads back. And then we'll use events to synchronize. So this is basically the same block of code that we saw in the demo. Send something down, process it, read it back. It's got a bunch of extra text. Let me break that out. So we copy down using the to GPU queue. We execute on the execute queue and read back on the from GPU queue. And we capture some events each time. So we have this copy event that is basically the copy kernel running, or the copy transferring to the GPU. And we tell the kernel launch to wait for that event. So it's enqueued, it's on the queue. It just can't start until the copy finishes. And then the same thing for the execute. We get an execute event. We don't copy back until the execute actually finishes. And when we do this, so this is an example that I pushed up without any overlap. These are my 3 queues and when they're busy. I had to use the CPU device because in OpenCL I had an NVIDIA driver, but NVIDIA doesn't do this as simply as this. And I didn't want to complicate the example. So I used the CPU device to force it to happen, but it's a multi-core machine. And there's no overlap in any vertical space. This is all in the same queue. So all the events happen together. It takes about 0.7 seconds to run to basically sum 2 vectors. I forget what size, maybe 10 megs. And then if I use this overlapping queue, right, I've got solid compute in there, and it takes about half the amount of time. On the GPU, this could be more extreme. In this case, there's a lot of CPU contention because it's trying to copy data from one place to another while operating on data and then copy it back out. And so there's a lot of data movement that doesn't really relate to compute. But we get this nice overlap of all the things going on. So it works in that sense. And it is faster. All right, questions about multiple queues? And with the events, it's not too hard to use them. The example is a little bit hairy because I wanted to, in the GitHub repository, because I put in the ability to turn off the separate queues, but the general framework is there. Yes?
So when you say wait for events, it's like waiting for the first item in that queue to finish and then the first one in the next queue to go, or how does it work?
It's actually, there's an event for each square. And so this green square is waiting for the event associated with that blue square. And then likewise green to red. So there's a chain, it's basically making explicit that dependency chain that we looked at before.
This is, if the other way is so much more efficient to do overlap, why is that the default?
Why not do this all the time? Why isn't it the default? Because it's complicated. You have to say, you have to be explicit about what your dependencies are. And so it just makes it harder to use. And often it doesn't, it's not necessary, it's not often, but in many cases it's not necessary. You launch a very large computation like a deep learning classifier, you know, some convolutional net that's gonna take 1/10 of a second to run. And so the overhead in terms of, yeah, and you're gonna get back just a single integer or something like that, a class label. The overhead in terms of code to make it, to put in all your dependencies and say what depends on what, it's gonna be much more painful than just letting it run in the simple case. You could put something on top of OpenCL that does dependency tracking, right? Where you say, okay, compute this using this kernel. These are my inputs, these are my outputs, a sort of data flow thing. And where it would know, oh, I can't launch this until these copies are done. But it's to make it more accessible, I think. Also, it's nice in debugging sometimes to have a nice in-order queue.
So this is really only applicable when you have like a huge amount of memory that you need to transfer if you have multiple like kernels or jobs.
Is it only applicable when you have a large amount of memory to transfer in a lot of kernels? No. I mean, it's always useful, almost always, especially since it's not just the size of the data and you know, it's not just the amount of data you transfer divided by the bandwidth that tells you how long it takes. There's overhead for setting up the transfer. And doing this sort of overlap allows that, also amortizes over that, that overhead of setting up the, you know, while the GPU begins computing, you can be negotiating with the GPU for the next transfer that's going to happen. In fact, when I run this on the GPU, it's very hard to see anything because there's a lot of just blank space between all of the kernels, right? Instead of looking like this, there's just big white gaps everywhere because there's so much overhead in terms of, I'm gonna send you something, okay, here, go ahead. And so there's a lot of back and forth on the slow bus. And then the actual transfer is very fast because it uses this DMA blocked transfer that's very speedy. So in general, it's worthwhile. It's just whether or not your compute is long enough to make it worth complicating your code. Unclear. So it's something you do at the end, right? Make it work, and then make it work fast. Other questions about this? All right. All right, that's basically it for the lecture. 2 pieces of news from GPU land, well, in parallel programming land. One, a couple days ago, we talked about the Tegra K1. The new one's out. It's just kind of cool to watch this stuff. Now with 8 cores, again, like before it was like this 4-in-1, like this one extra like, hi, wait guys, wait for me. Now it's like got brothers. Like 4 cores and then 4 little cores. I don't know what you do with those. And then instead of 192, now it's 256 CUDA cores. You know, you can see them up there in there. You can even see the warp layout, right? We talked about how warps are 16 ALUs that then run double speed, so they look like 32, and you can see little groups right on there. Teraflop per second, if you're 16-bit. Half a teraflop still, though, in 32-bit, which is pretty cool. Yes?
So a CUDA core is like one set of ALUs?
A CUDA core is those little green and bluish squares. Yeah, it's one ALU, right? They come in groups of 16. They operate at twice the regular clock speed. So you can issue, basically you can do like 32 ads in one clock. They have what's called the tepid clock and the hot clock. So instead of the cold clock and the hot clock, they have the tepid clock, right? Because it would sound bad if we get the cold clock. No, you get the tepid clock, which also sounds pretty lame. So yeah, those are the ALUs, basically the little compute engines. And then there's some sort of scheduler, and they probably, I don't know what they're organized in terms of, I think they're probably organized in groups of 4, actually, I think is the new hardware. I'm not sure, actually, in this architecture. Anyway, not quite as good in terms of gigabytes a second as a full-on thing, but still, that's fine. You do a lot of, and this is the real, I mean, the hottest it ever runs is 15 watts, and it's the size of a credit card for the board that they're shipping with, pins out and stuff. I mean, it's bigger when you put it on its support structure. All right, kind of cool. So that's good news. This is kind of sad news, like 2 days ago. Yeah. So that's, oh well. But he did excellent work, and, we'll remember his name in the law that we all hate. But good guy. I read about his life. I reread about some of the things. Competed with IBM and stuff like that. It's pretty cool. Anyway. All right, next time, Adi is going to talk about lock-free algorithms. The rest of the semester is going to be lectures about lock-free and cache-oblivious algorithms and some other stuff like that. If there's a particular subject from parallel programming at a high level that you're curious about, post on Piazza. Maybe we can steer a lecture towards it or part of a lecture. Have fun with homework 3. Keep chugging along on final projects. I will see you next week.